Let's start the review with the backtracking search. And so I start just with this example that we had. So this was the map of Australia, if you remember, and these regions are, for example, this one was Western Australia, Northern Territory, and here is South Australia. And these regions on the right, the upper right is Queensland. Here we have NSW, and here we have Victoria. And then this one here, the small region, which is not connected to any other region. Now we want to color these regions in a way that no two regions that are neighbor have the same color using like backtracking. So we said that in backtracking, so you are, if you're not using any like forward checking, or arc consistency, so just a pure backtracking search, what it does is that you say, okay, now I have, if you're going, for example, from Western Australia, you check all your domain values. So for example, our values could be red, green, blue. So we say we have 3 options. So we can color this red, green, blue, and it doesn't violate any constraint so far because no other region is colored yet. So it is fine. We can color it either red, green, or blue. And so you just pick a region, assign a color, and then you go forward. And then let's say if you color this region red, and then we said with the next region, we have, let's say if you want to color, for example, the next region would be Northern Territory, and you want to color it, then you have 2 options, right? Because of the constraint, we cannot color it red anymore because we assigned red to this one. So this time we can either assign green to Northern Territory or we can assign blue to it. And then from here, again, we continue, right? So for the next, for example, region. Now, if for the next region, if it's, for example, Queensland, you can either assign red, right, or blue, because this one is green and no other neighbor has been colored yet. So the only constraint is that Queensland should not be green, and then you have these 2 options. However, if you continue like this, now at this point, you reach a failure in your search, right? Because if you color Queensland blue, now if you look at South Australia here, you have no options left, right? No value is left to color this region because it cannot be red because of Western Australia, it cannot be color green because of Northern Territory, and it cannot be blue because of this region. And so this is actually just an example of how backtracking systematically finding a solution, or maybe it just doesn't find any valid successor, so it failed and then backtrack. So if you reach here, then you have to backtrack, right? Because this was a failure. So we say we assign another color to this. If there was also none of the colors actually reach to a solution, or like all of them are failure, then you backtrack to the previous variable, right? And then you choose another color for the previous region. And then we also talked about how we can improve backtracking efficiency, which variable we can assign next. We said we always use minimum remaining value heuristic, right? There are different heuristics you can use. So minimum remaining value was one heuristic. And then if there was a tie, for example, if there are 2 regions, 2 variables with the same minimum remaining values, that is 2 regions with the same minimum remaining colors, then you go with degree heuristic, right? So this is to answer question 1. Question 2, in what order should its value be tried? For example, when you reach to a new region, how do you know, for example, if there are 2 colors available, red and green, how do you know you have to, for example, use red or green, right? So choosing the values in your domain, or choosing, for example, the color in our example, is answering this question. How do we do that? Using the least constraining value, right? The LCV. So that is what actually you choose a color that puts less restriction on other neighbors. Okay, so for example, I'm going to show you on a map that if you, for example, reach to a situation that there is, for example, 2 colors left for a region, if you want to pick which one to choose, then you want to see choosing a color that puts less restriction or gives more flexibility in terms of assignment of colors to other regions or neighbors. And then can we detect inevitable failures early? Yeah, there are several ways to do that. We can use what? What are the methods that we discussed to maybe see those failures early? Forward checking was one of them, right? Because in forward checking, we said instead of like going into like one path and then see, okay, this is a failure, and then backtrack, trying another one, and then lots of backtracking. So forward checking, look one step ahead, and then it says, okay, if you assign, for example, red to Western Australia, now you have to check for all its direct neighbors and then remove red from all the neighbors, not only the next one that you want to assign the color, right? Because in backtracking, we said, okay, we start from, for example, Western Australia, we assign red, and then if next one is Northern Territory, we cannot assign red, and then we did it, for example, for another one. So we did it one by one, and there were lots of backtracking then. But now forward checking says, okay, you can avoid that like failures, not all of them, some of them, by looking one step ahead, so that if you assign, for example, red to Western Australia, now you want to like check all the neighbors. So if Western Australia has 2 neighbors, so you remove red from both neighbors at the same time. And there was also another method, arc consistency, right? AC3, which was even more efficient in terms of finding like more inconsistencies, because instead of looking one step ahead now, you look like the whole, you check for the consistency between like all the arcs, right? So for instance, I'm going to show you again in the example that if you, for example, remove a color from a variable, from a region, let's say you assign red to some region, and then you want to like, if you have removed a color from a region, you want to make sure that there is at least one value left for other regions, right? So let's see these in example. So for example, in the answering the first question, that which variable to choose next, we said that we go with, for example, minimum remaining value. That is, you choose a region that has fewest colors left. So for example, if you have 2 regions, one of them is left with 2 colors, one with only one color, you choose the one that has only one color left. So I think in this example, we started from Western Australia and then colored Northern Territory green. And then we had option to either choose this one, right, which is Queensland, or choosing South Australia. So how do we decide, choose this one or this one? This one has only blue left, and this one has blue and red left, right? So we choose the one that has less value left, which is South Australia, right? Because now if we choose this one, we know that we can only assign blue to this, right? So this is fixed and we get rid of it. And then there will also only one value remains, for example, for in this region. While if you go with this one, if you go, for example, with Queensland, because there are 2 values left, right? If you choose this one, then you have like more explorations ahead. So you always, the minimum remaining heuristic value heuristic tells you choose a variable with the fewest legal values. So for example, here, choosing South Australia because it has less colors left. Now, there was a problem that maybe, for example, sometimes we have 2, for example, regions that are left, for example, with the same amount of color, and then what should we do? And we said, okay, in that case, if you reach to a region, to a state where you have, for example, 2 regions, and both of them, let's say, left with only one color, which one to choose? You choose the region that has more impact on other variables or regions, that is connected to more regions, because coloring that region affect more number of regions, right? And so it reduce options or values also from the domain of like all those neighbors too, right? And so, for example, after you color, we color, for example, South Australia here and their Northern Territories. So now both Western Australia, right, and Queensland, they both are left with one color, right? So how many colors are left for Western Australia? One color, red, right? How many colors are left for Queensland? Can I color it green? No. Blue? No. So only one color left. So these two regions, they both are left with only one color. So whenever there is a tie and you cannot go with minimum remaining value to choose the next variable, then you can choose it based on a degree heuristic. And that means you choose the region or the variable that has more impact to the other regions or is connected to more neighbors. So in this case, Western Australia is only connected to these two regions. And this is connected to like more regions and is affecting more actually even unassigned regions. So we pick this one to color. Now we have answered the first question. We know how we can choose the next variable, right? So we go with the minimum remaining value. If they have both, like there are multiple variables having the same minimum remaining value, then we use degree heuristic to break a tie. And now for deciding which color or which value to pick or answer the second questions, we said that we can use least constraining value. That is choosing the value that rules out the fewest options for future assignment of future variables, right? So for example, let's say we started with Western Australia red and then again we colored this Northern Territory green. Now we also said that we want to pick this one, right, to color. Now which color to choose? We can color it red or we can color it blue, right? Now deciding which color, we go with least constraining value. It is, you see if you assign red to this region, how many options are left for the next neighbor that you want to like color, right? So if you assign red to Queensland, what are the options for South Australia? If you choose red for Queensland, what is the option for South Australia? One option, blue, right? So we only have blue left here. Now, what if you color it blue? What if you color Queensland blue? What are the options for? No option, right? Because then South Australia is here, stuck with like not allowing having like red because of Western Australia. It cannot have like green because of this region here, and also it cannot have blue because of Queensland. So we pick the one that have actually least constraint on others. So this one allowing 0 value for Southern Australia, it means that it has more constraint on Southern Australia, right? So we pick this one because it gives least constraint or more flexibility for the next region. And we saw that in backtracking, we often reach to, for example, failure in one branch, and then we backtrack, and then we said, okay, how can we, is it possible that we avoid or kind of like predict like these failures earlier? And as your friend said, yes, we can, using, for example, forward checking or R consistency. Now, reviewing forward checking. So we are going to, so as soon as we assign a color or assign a value to a variable, as soon as we assign a color to a region, we see the impact on all its direct neighbors, okay? So if, for example, you assign red to Western Australia, what are the direct neighbors? Western Australia? Northern Territory and South Australia, right? So as soon as you assign a color to a region, you have to update its neighbors. So the neighbors cannot have red, so you remove red from the domain of other variables that are neighbors to this, or other regions that are neighbor to this one, right? So you remove red from Northern Territory and South Australia. What is the difference with backtracking? What would have be done if we wanted to just do backtracking without forward checking here? I want to see if you've seen the benefit. I really love your enthusiasm for answering my questions. Yeah.
So here
Sorry.
in this one, we have excluded the options for the next step beforehand, but in backtracking, we go to that step and then we see if that option does not exist, then we backtrack.
Yeah, and in backtracking, we are actually like going to assign colors, and then if we actually do the assignment, for example, we assign red, actually we go one by one. We are not, for example, here we say, okay, we assign red to Western Australia. We checked for all direct neighbors. Here we have 2 neighbors and we remove red from both of them. But we don't do any assignment here. We just remove the possibilities and we reduce our search space, right? But when you're doing backtracking, what you do is that you're going actually one by one to the neighbors. For example, you go to Northern Territory, assign a color, and then you see, okay, it is not possible. And then if you reach a failure, you backtrack. Like, for example, the examples that we've seen with backtracking when we reach to a state where, for example, if we colored that region, there was no other colors left for the other region. So forward checking, just avoid that by looking one step ahead, right? And why one step ahead? Because we're just seeing the direct neighbors. We don't go any like deeper, right? We just see the impact on this one. Now, let's go to the next one. Let's say we color, for example, Queensland green now. So you already assigned red here, which removed red from Northern Territories and South Australia. Now, if you also assign green to Queensland, it means that you have to remove green from all its direct neighbors, which are Northern Territory, right, South Australia, and New South Wales. And so you have to remove green from these 3. Now, if you remove green from these 3, this is what you'll get. So there is only blue left for Northern Territory, blue and red left for this one, and only blue for Southern Australia. And now, let's say Victoria is blue, then you also have to remove blue from the neighbors of Victoria. And then it will be like, for example, no blue here, right? So NSW, you remove blue from here. And you also have to remove blue from South Australia, right? Now, this is a problem. There is no valid options or valid colors left for South Australia, right? And now, if I go one step back, so this is, I want to also mention a limitation of forward checking now. If I go one step back, you can even realize it from here, right? That there is going to be a conflict because now there are 2 states that are neighbors and both are remained with the same color left. So there are Northern Territory here, right? And then South Australia here. Both of them remained with blue, and they are neighbors, right? So they cannot have like the same color. This is what forward checking cannot detect at that level. So it continues. If you see, it continues with, for example, Victoria. It continues until it reaches, for example, here, that we don't have any colors or values, valid values left for South Australia. But on the other hand, the advantage compared to just like using backtracking is that instead of like continuing down an invalid path, right, and do like several assignments which are not valid, and then later we have to backtrack, here we are just immediately doing the backtrack and try different color assignments earlier, right? And so we said the problem with forward checking is that it just eliminates the values from the direct, from one step ahead, or for example, removing colors from only the direct neighbors without actually checking for like other regions. So it doesn't detect any deeper conflicts. The solution is, for example, with some other constraint propagation, such as arc consistency. So with arc consistency, it repeatedly enforces constraints. So instead of just looking one step ahead, so now you are iteratively enforcing the constraint across multiple variables or multiple regions in this example. So it just doesn't just check the direct neighbors this time, but also checking all throughout the network. And then we said that in our consistency, if you remember, we said that, for example, x implies y, where these are your variables. Let's say there are two regions. They are consistent if, for example, for each value that is, for example, when you remove a value from, for example, x, you want to make sure that there is at least one value left, right? There is some value for y, right? And so here is, for example, our consistency. This is the definition. So we say x, y is consistent or are consistent if and only if for every value x, so this is each value in x variable, there is some allowed y. And we'll see what that means. So for example, if you are removing a color from a region x, then you want to make sure that there is some values left for other regions, right? And so here we started with, for example, for the we want to like explain the arc consistency here. So we started with color in Western Australia red, and then Queensland green, right? And then we said at that state where this is red and this is green, the Northern Territory and South Australia remain with only blue, right? And then New South Wales is remaining with red and blue, right? So now here, every value, so our consistency, for example, between NSW and SA South Australia means that if you remove a value, for example, remove color blue from NSW, you want to make sure that there is at least one valid or some valid value in South Australia domain, right? So now since South Australia has only is only left with blue, so it means that NSW cannot be blue, right? And so because NSW and SA are adjacent, right? So here is NSW, here is SA. So these are neighbors, so they must have different colors, right? So if this is blue, this cannot be blue. So you remove blue from the domain of NSW. So you remove blue from the domain of your X, right? So this is your X, this is your Y, or this is your XI, this is your XJ, doesn't matter. So you remove it from here, right? Now, as soon as you remove a value from the domain of NSW or from the domain of X, the arc consistency tells you that you have to check that you have to continue, right? You don't stop here. You want to now make sure that there are some possible values left for other regions as well. And so what does forward checking here would have done if you were doing forward checking?
Would have proceeded until it found no legal values for a certain country, and then it would have backtracked?
When you assign these colors to Western Australia and Queensland, right, it just checked the direct neighbors, right, and then only remove the values from the direct neighbors, but doesn't go any deeper, for example, to this region, right? While with the arc consistency, you see that now we are going to check all of them. So now, because New South Wales, NSW here, because this lost a value, because we removed blue from here, now we must check all its neighbors again. So we don't stop there, which was the case, for example, with forward checking. And now, in particular here, for example, Victoria, which is here, and is neighbor with New South Wales, Victoria cannot have green, right? Because NSW is left only with red now. And Victoria is neighbor with it. So Victoria cannot be red, right? Because this is only left with red. Because of the same reason that here we said that NSW cannot be blue, right? Because South Australia, which is the neighbor, is left with only blue. Therefore, NSW cannot be blue, so we remove blue from here. Now, because blue has lost a value, you have to check other regions that are neighbor to NSW, which are, for example, Victoria. And now Victoria also cannot have red because this region is only left with red. And so red is removed from Victoria. And just note the direction of this arc consistency here, right? Here, this is your X and this is Y. And here we remove a value. You always remove a value from X, right? Now you remove a value from Victoria. So you remove red from this region. This time, the arc consistency was between NSW. So this was your X and this was your Y, right? And then you remove the value from NSW. And then you remove red from Victoria here. And then you go next step. Now here, South Australia has only one remaining value, right? This only has blue. And then Northern Territory has also one remaining value, blue, right? And then South Australia and Northern Territories are neighbors, right? So they cannot both have the same color, which means you have to remove blue from one of them, right? So South Australia, which had only one color left, if you remove this from South Australia, it means that it doesn't have any color left, right? So you realize with arc consistency that if you, for example, do these assignments, you have a failure because these two regions are neighbors and they cannot left with one color that is the same, right? This is what forward check didn't realize. So when we did forward check, we reached this step, but because at that stage, it didn't check any consistency between South Australia and Northern Territories, right? It just moved to Victoria. That was the direct neighbors at that time. And then after it assigned a color to Victoria, and then we saw, okay, now we don't have any colors left with this one. While when you do the arc consistency, you actually realize it at the beginning, right? Because you continue, you don't stop. As soon as you remove a value from a variable or remove a color from a region, you continue check for all its neighbors. Now, you update the colors of the neighbors, which means that you have to remove some colors from the neighbors too, right? Now, because you remove the color from those neighbors too, you have to again continue because whatever region that lose a color, you have to check its neighbors. So for example, this time we said NSW lost the color blue, right? So we have to check its neighbors. And then we said, okay, Victoria, now we check for Victoria, and we said, okay, Victoria cannot also be red because this is only left with red. Now we have to check for all neighbors of Victoria, and then we continued. Now, which are, for example, SA and NT, right? And then you had to check the arc consistency for these ones, and then you realize that they cannot have the same colors left. And so this is just a comparison. So in forward checking, when a variable is assigned, a value, FC or forward checking just remove conflicting values from the direct neighbors, right? While with the arc consistency, you repeatedly check constraint between variables, right? For example, when we removed a color from NSW, we didn't stop there. We checked the neighbors, which was, for example, Victoria. And then we said, okay, now Victoria also we should remove red from Victoria because NSW was left with only red and they are neighbors, so we remove red from Victoria too. And then we have to check the neighbors of Victoria. And then if they're fine, still we're having continuing for all the neighbors, right? And then we go, for example, to neighbors of Victoria, which are South Australia, right? And then South Australia with Northern Territory was also neighbors, right? And if you remove a color from, for example, South Australia from, for example, Northern Territory or the other one remains with no values left, with no colors left. And so with arc consistency, you realized it much earlier. And so can you tell me now, in terms of, if you want to say in terms of time complexity, which one has a higher time complexity? Arc consistency or forward checking?
Arc consistency?
Yeah, arc consistency. Why?
Repeatedly checks every time?
Yeah, because we're not just checking the immediate neighbors, but we are constantly, we don't stop there, right? We constantly check. As soon as we remove a value from a variable, we are checking its other neighbors, and we continue so on. Now, can you tell me when you want to like use, for example, arc consistency compared to forward checking? Let's say if, for example, if you have a small domain, okay, if your size of your domain is small, which one would you choose? If domain is small, you choose arc consistency, and why?
Because the time complexity is large, so if the domain is small, it won't take as long.
Yeah. While, for example, if your domain is large, then your time complexity, which depends on the domain size as well, right? So the time complexity increase as your domain increases, right? What is the time complexity of AC3? Let's do it with forward checking first. What would be the time complexity of forward checking? Let's say we have n constraints or n edges or constraints, and the domain size is d. N multiplied by d, right? So you have n constraints. You also have your domain size also. For example, you can assign red, blue, green, right? Your domain size is, for example, 3. Then it will be n multiplied by d, which is your domain size. And while this can go exponential for AC3, right? Because you have like iterations, and then the first one is multiplied by d. The second time, again, you're adding another multiplied by d, right? So it's going like exponential d to the power of 2. And the next time you want to like go for the neighbors again, is go to d to the power of 3, right? And so in terms of time complexity, as you increase the domain size, the AC3 may not be that efficient anymore to go with, right? So you want to go, for example, with forward checking if you have large domain size, and use it with backtracking just to reduce your search space a little bit.